So the last part of this chapter reviews the calculus of several variables. Okay, and there are many books that you could read for this, but the one that I prefer is Kaplan. Kaplan is a famous professor in applied mathematics. Okay, at I think in America at University of Chicago, Ann Arbor, the same place as Churchill. They're the authors of the complex variable text that we used in second year. Okay. First here we look at the definition of continuously differentiable of the real value function of n variables. In optimization, we are dealing with real values, real functions of n variables. Okay, it can be the objective function or the constraint function. They are all real functions of n variables, where the desired variable x, has dimension n. So here, so a real value function f of n variable is said to be continuously differentiable at a point x. If all partial derivatives with respect to xi exist and be continuous for all I. And the notation that we use is that when f is, so we write f belong to the class C1. C1 means continuously differentiable at least one time, at least once, and this is why we say C superscript 1. Okay. So what happens when the function f is continuously differentiable? You can see that the gradient of f with respect to x exists. Okay, and you already know what is gradient vector, right? From calculus 3. Yes or no? Sure. Yes.
Yes.
Okay. I think in the new curriculum for undergraduate, I think there will be, they took only 2 courses for the compulsory courses. I don't know why, but okay, that's the future. Okay, and then we look at in a similar fashion to the above definition, we look at the definition of twice continuously differentiable. Then the function f, the function f is said to be twice continuously differentiable at the point x if the second partial derivative with respect to xi, xj exists and continuous for all ij. Now you see that when for a real value function of n variables, this how many second partial derivative? N squared, right? Because this is the partial derivative with respect to xi, xj. It is second partial derivative. And what? And we use the notation f belong to the class C2. So the class C2, the superscript 2 represents how many times we can how many times the function continuously differentiable. Continuously differentiable means we the derivative after differentiating the function, then the derivative is a continuous function, and this is what we call continuously differentiable. When the function is differentiable, the derivative may or may not be continuous. But when the derivative is continuous, then the function is said to be continuously differentiable. Okay. And So what is the consequence if the function f is twice continuously differentiable? We find that the tension matrix or the second derivative matrix defined this form exists. And as a consequence of continuity of the function, then when the function f is twice continuous, when the function f is twice continuously differentiable, then you see that the partial derivative, the second partial derivative of f with respect to xi and xj is equal to the partial second derivative of f with respect to xj and xi. So we can swap, or we can swap, or we can change the order of the partial differentiation without making any difference. Okay, but we can only do this only when the function f is twice continuously differentiable. Okay, this is, we use the continuity property in calculus. So that means, so for the when the function f is twice continuously differentiable, then the Hessian matrix is always symmetric. Okay, so in chapter 4 and chapter 5, when we are dealing with unconstrained optimization, you will see that the Hessian matrices are always symmetric because we consider only smooth functions. Okay. And when we in our chapter in chapter 4, when we consider optimality conditions, then we will apply the basic knowledge of this to find necessary and sufficient conditions. Okay, we find necessary conditions and sufficient conditions for optimality in chapter 4 later. Okay, the next topic, okay, which is the last one on this, is the Taylor series. Actually, Taylor series are very, I think, are important, very important. And I think at this, for engineering students, I think you may not see this, okay, and now, but when we use, but Taylor series is very useful. Taylor series are an important tool in mathematical analysis. Okay, when we derive, if you analyze when you do the mathematical analysis, okay, you will find that Taylor series, we often use a Taylor series. Now we look at the Taylor series in one-dimension case first. So in one-dimension case, f maps R to R. Okay, f is a real value function of single variable. So in this one, then we come up with the mean value theorem, which is a special form of a Taylor series. Okay, the mean okay, so the mean value theorem states that if f is continuous on the closed interval from A to B and differentiable on the open interval from A to B, then there exists a number lambda in the open between A and B, such that FB is equal to FA plus A prime lambda multiplied with B minus A. In this form, okay, this is now you see that there exists a number of this, but then the meaning may not be clear from this. But if we rearrange this, then what we have, after rearranging this, then you see that the F prime lambda is equal FB minus FA divided by B minus A. Right? So what does it mean? It means this is A, this is B. Okay, this is the function F. Right? This is the function F. So if we what is this? This is FB minus FA. Right? Right? And this is B minus A. So FB minus FA divided by B minus A is the slope, right? Of this. Is the slope of this. That means you see that F lambda is equal to the slope. So at the point lambda, the derivative of F is equal to the slope of this, okay? Then that means there exists a lambda somewhere here. Slope of the green line is parallel to the slope of the red line, this red line. That's the meaning of the mean value theorem. In another representation. Okay, now we consider the Taylor series in suppose that the function f has n plus 1 continuous derivatives. So that means all the n plus 1 derivatives of f are continuous function. Okay. Then what we have is that f of x naught plus s can be expressed as linear combination of the function f and all derivatives of the function f at the point x naught. Okay, so fx naught plus s is equal to fx naught plus s f prime x naught plus and so on up to the s to the power of n divided by n factorial f the n derivative of f at the point x naught plus the last term is called the remainder term, which is a little bit different from this one because you see that now here we have s to the power of n plus 1 divided by n plus 1 factorial multiplied with the n plus 1 derivative of f at the point cosine. Now cosine is an extra variable and cosine is cosine is a point between x naught plus s. We don't know what it is. So in many applications, you will see that this term, the term with extra variable, will vanish after we do the algebraic manipulation. This is what happened. You will see this very soon in chapter 4 or even chapter 3. Chapter 3, we use that as well. Okay, when we analyze solution of nonlinear equations. Now at this point, you see that now we will after this we will extend this to the case of n variables. For the case of n variables, then we represent how can we represent this for a vector x? okay, with n dimension. So we cannot write it in this form, right? Because this notation only valid for scalar variable. This notation is only valid for scalar variables. Okay. Then when we want to extend this to the case of the vector, okay, into the vector case, then we cannot use this notation. So what we do is that we write it in an equivalent form, but in this new form, we can extend this to the vector case, right? So this is how we express it. We express it as the variable psi, we write the sign as x naught plus lambda s. X naught plus alpha s. Okay. X naught plus alpha s, where alpha is a real number, which is between 0 and 1. When alpha is equal to 0, right? Then the sign is x naught. Right? And then when alpha is 1, then the sign is x naught plus s, right? So this is what we want. But now you can see that this can be extended to the vector case in a straightforward manner. Okay, now we see the multivariable case of the Taylor series. In this case, f is a real value function of n variables. And now with when we adopt the vector and matrix notation, we can write, now you can see that the vectors are written with the bold type, bold font. Fx naught plus s is equal to fx naught plus s transpose grad of fx naught plus 1 over 2 s transpose, the Hessian matrix of the function f at the point x naught multiplied with s plus dot dot dot. Dot 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 means is high order term. In our course, we need the expansion. We will expand this up to the second order term, and that's what that's all we want, and it's enough. Okay, let's say that's enough in our for our consideration. But if you want to write it in using summation, then this is this is it. You see that now. If we this is what we call this is the first order term. Okay, the first order term means the term involving the first derivative or the gradient, and the second order term means the term involved with the Hessian matrix. And how about the third derivative? Then it's very complicated. Okay, but we consider only up to the second order in this course, and that's enough. Okay, and so we consider again the mean value theorem. In the mean value theorem, assume that f is a real function of n variables, and the function f is continuously differentiable. Okay, in Rn space. That means it's continuously differentiable for every point x in Rn space. And then fx naught plus s is equal to the fx naught plus s transpose, the gradient of the function f at the point x naught lambda s, where lambda is between 0 and 1. Okay, and this is what we call the differential form of mean value theorem. Whereas I think, okay, the mean value theorem can be also expressed in the integration form, the integral form, which I think that, but this is usually, I think people get used to this more than this, but this is something as well. So I put it together here in the review. So fx naught plus s is equal to fx naught plus the integral from 0 to 1 of s transpose by fx naught plus ts dt, where t is the dummy variable in the integration. Then when the function f is, okay, when the function f is in the class C2, so that means when f is twice continuously differentiable, then from this theorem, we can prove that fx naught plus s is equal to fx naught plus s transpose by fx naught plus 1 over 2 of s transpose, the hedgehog of the function f at the point x naught plus lambda s multiplied with s. Okay, and the lambda is a real number between 0 and 1. Now what happens? You see that when in this function, you can see that in the second derivative term, this is what? What is the form? This is a quadratic function. It's the 1 over 2 s transpose multiplied with a matrix, right? And multiplied with s. Okay, in subsequent analysis, we will have, you will see that we focus on the positive definite property of this matrix. Okay, that will be in chapter 4. This is a quadratic form, right? S transpose AS is what we call the quadratic form. Okay, quadratic function. So, and this is the end of the chapter 2. I think we will have time. So when we have time, then I think we can spend 20 minutes on the next topic. Right, we go right to the chapter 3, which is the starting of this optimization course.